ABC Calc students, this is going to be day 11 notes, and this should be the start of the next packet, so make sure you have that out. So get ready to take some notes on today, parametrics, velocity, and acceleration. So we're going to be getting into really some applications of derivatives here and how the derivatives of certain functions might result in a new function that represents a velocity function or an acceleration function. So before we get into that, let's take a look at the product rule that we all know and love at this point, right? That the derivative of u times v is equal to uv prime plus vu prime. And right underneath it, it says, well, see if you can develop a rule for the product of three terms, u times v times w. And I'm kind of giving you a little bit of a hint here that maybe you can develop it by separating it into the product uv times that third variable w, that third function there. All right, so maybe if that's your hint, you can try and see if you can develop this rule if we have three functions that we're multiplying together. Here's kind of what I came up with. So if I applied the product rule to this times that second quantity there, it would be the following. So I wound up writing it as the first times the derivative of the second plus the second times the derivative of the first. And I know sometimes we kind of reverse that order, but with the sum, we can switch the order and not worry too much about that. Well, since we have a derivative of a product here, we have to use product rule again. So we get something that looks like this, right? This would be u times v times w prime plus w times this result over here. So after distributing the w, you might get something that looks like this, uvw prime plus u prime vw plus uv prime w, right? So it's essentially the product of the functions where in each instance, one of those functions derivative has to be accounted for. So you can imagine if I had, 27 functions that we were trying to multiply together, that, we'd have a list of 27 terms going across here, where in each case, only one derivative was being found and then multiplied by the others. Okay, so just kind of a quick, nice way to develop that rule in case we had three functions instead of just two that we're multiplying together. So to get into our discussion of velocity and acceleration, we're going to start talking about rates of change here, right? And we know that average rate of change is just slope. So if we're looking at a graph and when I ask you for the average rate of change, that's the slope of the secant line, right? A slope delta y over delta x that connects those 2 points. But meanwhile, if we then talk about an instantaneous rate of change, that's going to be the slope of the tangent line, right? That's the slope at a given moment, at a given point in time. So that in this case is the limit as delta x goes to 0 of that slope, which we know results in a derivative. So just the difference between average rate of change, slope of the secant, instantaneous rate of change, slope of the tangent line. So here's a good example. A sprinter runs 100 meters in 10 seconds. That sprinter's average rate of change, 100 meters divided by 10 seconds, would be 10 meters per second. Which happens to represent the average velocity. But what if I wanted to know the instantaneous rate of change? So in other words, if I wanted to know what is the runner's velocity at 5 seconds into the run, we need a way to be able to determine that, and it involves, of course, derivatives, right? Slope of the tangent line at that point along the function. So I actually have an article that maybe I'll try and share with you in class tomorrow about Usain Bolt and some of the calculus behind some of his runs and when, at what moment he was increasing and he was at his fastest rate of change. Because we can certainly calculate his average velocity pretty easily based from start to finish. But at what moment during the race was his velocity the fastest? So we can kind of get some time and look at that. All right, so if we're okay with average rate of change and getting into instantaneous rate of change, on the next page, we have an application that we'll model together. The example says, how long will it take a billiard ball to fall 100 feet? Well, a couple of quick things that we have to reference before we get into this question. One of them being that we're going to neglect air resistance. And we're going to use the model S equals 16t squared. So this is because the AP exam uses English units. So I apologize to all my physicists out there who are like, no, Mr. All, we want 9.8 for meters. But we are going to use the function s equals 16t squared. So to figure out the time that it takes to fall 100 feet, where s is the position, let's just plug 100 in for s and solve there. So we get 16t squared is equal to 100. Divide the 16 over. Okay, 100 over 16 would reduce to 25/4. Square root. And since we're dealing with time here, we don't really care about the negative aspect of taking the square root of both sides, but t is going to equal 5/2, or probably means a little bit more to us if we say it takes 2.5 seconds for this to happen. So the nice thing that we can do on our calculators is we can represent this scenario parametrically. So if you don't remember how to use parametric mode, I know this is something you would have learned in the spring, so maybe you were a little bit shaky with it. But I'm going to show you real quick. If you go to your mode on the calculator, make sure that you have parametric selected so that we can type in this sample scenario. Then if you hit y equals, you'll see different lines for x1 of t and y1 of t. And there's two things I'm going to have us type in. So I'm going to type into x1, I'm going to have that equal to 2. The reason why we're using 2 is to move it off the y-axis to simulate this object falling. Oh, and by the way, we should probably put a negative in front of the 16t squared so that the object does in fact fall down. Okay. So if we go to x1t and type in 2, y1 negative 16t squared. Remember that t is going to be the same button that you use to hit x in function mode. Okay, so that's how we get our t. A couple other things that we might want to consider is we should probably set a window for not only x and y, but we need some t values in there as well. So t, we're going to range from 0 to 3 in the window. Hit window. Right now mine's 0 to 10, so we'll do 0 to 3. The x values, I mean, 0 to 10 should be fine since we have x equals 2, but I'll play the game. Negative 10 to 10 there, and for y's, we've got 10 to negative 150 for our y-min. Okay. So with all that being said, I also had the graphing style selected as kind of like this little bubble guy here. So if you go back to y equals, Mr. K very lovingly called this bubblicious, which I love. So you might want to change that graphing style out here in case you want to make it appear that, yeah, this is a ball falling. All right, I think I've set the stage here that if I hit graph, there it is. All right. So again, the only reason we have x equals 2 is because otherwise it would be right on top of the y-axis there, and it'd be really tough for us to see. That's the only reason for that. So that happened pretty fast, and I guess if we wanted to slow things down, what would we have changed to slow down the motion? So think about that for a sec, but what could I have changed so that maybe if this happened too fast, or if I'm doing another problem and I'm like, wait, I didn't see what happened, what do we want to change? How about the t step? I didn't reference that when I typed our values for t into the window there, but the t step is, you know, how often we're plotting a value as far as t increases by, I think my t step was 0.1. Yeah. So currently my t step is 0.1. If I cut that in half to make it 0.05, that's definitely going to slow down the motion because now it's going to plot more points along the way for every value of t in increments of 0.05 as opposed to going up by a tenth each time. So if I hit graph, I think we should see this slow down a little bit. Yeah, that looks nice. Okay. So don't be afraid to mess around with the t-step if needed so you can easily see what's going on there. All right, let's keep the party going with some parametric mode here. So we can also simulate not only vertical motion, but horizontal motion. If we take a look at changing our x1 value to the following 4t cubed, and then minus 16t squared plus 15t. And then in y1, we're going to make that a 2. Again, this is just to move it off the x-axis in this case. We've got bubblicious selected. There is some window suggestions that I have for us here. So let's make us go from 0 to 5. We'll look at this for a span of, let's say, 5 seconds. Let's say the t-step at 0.05. -4 to 6 for x min and max, and then -3 to 6 for y min and y max. Okay. So if you have your window set up that way, let's go ahead and hit graph and see what happens. And oh, this object is moving now, yeah, horizontally. Now here's the issue though. I've seen the graph, and now that the graph is finished, how do I know where it changed directions? Okay, so if we type it in this format, I'll tell you it really is tough to see when it changes direction, which might be something we're concerned with, right? How much time does it take to go in the other direction? All right. Well, there's ways of fixing that. So if you keep what you have in x1 and y1 there, but go back to y equals, and in x2, I want you to enter x1, so it's going to recopy this over for us. And then in y2, we're just going to type in t. Okay. So to get x1 of t, what you would do is a couple different ways to get it. I think the most concise way is alpha trace. So alpha trace gives you all your variables that we're using for parametric mode here. So let's just enter x1 of t there, come down to y2 and type in t. I also think my mode is in simultaneous mode, guys. So if you want to switch that over, this is going to graph both at once. It's up to you. It did suggest that we should have it in simultaneous mode, but let's see if that makes it any better as far as seeing in the end where it changes direction. So if I hit graph, yeah, there was the original, but now I can really clearly see that if we're not just changing it to a horizontal height, if I let y equal t, we can more easily and better see when this object would change directions. So that's kind of a nice aspect there. And then the only difference in this case is if I switch them up and I put x1 of t as my y value here and t and x3, maybe you can guess what's happening there. If I put t down here and then again make this alpha trace x1 of t, you'll just see that it changes to vertical motion. All right. So a couple good options there if we're trying to analyze graphically when something changes directions, things of that nature. Okay. All right, so here's an example that I think would be nice to try. Dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height s of t equal to 160t minus 16t squared feet after t seconds. So it says solve parts A and D graphically, and then after that you can confirm with part C and D analytically. So here's what I'll say. You know what? Go ahead and try this one. And I think this will be worth our time to go over in class tomorrow. So see if you can simulate the rock moving. So that would be involving, see what you can do in parametric mode to make this happen. Graph the rock's height as a function of time. And then see if you can answer these questions that go with it, okay? And again, I think this will be something we can maybe quickly recap tomorrow. Okay. Going on to the last part of the lesson here, we have the difference in speed versus velocity. So speed is a scalar quantity known as a magnitude. Velocity is a vector with magnitude and direction. I love watching that clip from the movie Despicable Me where the evil villain Vector just defines himself as being a mathematical quantity with magnitude and direction, okay? So what's the relationship here? Well, speed is the absolute value of velocity. That's how speed is defined. And again, if physics students, I'm sure this is stuff that you're all very familiar with, but what that means is that when we're talking about speed, this makes sense, but speed is always a positive quantity, okay? It has nothing to do with direction. Then as far as acceleration goes, acceleration is the rate of change. Rate of change would be a derivative of velocity. So there's some really cool stuff that goes on here. Acceleration is the derivative of velocity, and that would be then the second derivative of position. And if you like this Newton notation a little bit better, we have a of t equals the derivative of velocity or the second derivative of position. Okay. So as a quick recap, we know that position is negative 16t squared. And therefore the derivative of that, using the power rule, would be negative 32t, and the derivative of that would just be negative 32. And this is what we know to be the gravitational constant, right? Negative 32 feet per second squared. So I think that's kind of a cool way to be able to develop this concept. I know it's probably a little bit bothersome for physics students, but we'll get used to it and we'll stick with our English units in this class. One quick note is that if you have any questions about some of the homework problems, there's questions that involve derivatives in economics. And I think the textbook kind of assumes that you've read the section that has information about cost versus marginal cost. Okay, so marginal cost is the derivative of an average increase in cost. So if you look through that just really quickly on pages 206 and 207, I think that will help you to answer some of the questions in the textbook. Okay, but I promise we'll do a really quick recap tomorrow and go through this question about the rock being launched in the air. And if you have any other questions in the meantime, let me know. Have a great day.